We're going to continue with another geology topic. We're going to move past the rocks and minerals, and last week was the weathering and erosion, more surface feature stuff that occurs with geology. What we're going to get into from now until the next couple units anyways, I think is the more dynamic parts of geology. Starts with plate tectonics, then it moves into plate boundaries, earthquakes, volcanoes, that kind of stuff, which I think is pretty cool. Let's get into this then. Capital letter A. In the year 1915, a scientist, his name was Alfred Wegener, but it was spelled W-E-G-E-N-E-R. It's a German name, basically, although he spent a lot of time in America. He proposed a hypothesis that Earth's continents were once together as part of a supercontinent, and he called that supercontinent Pangaea. I've seen it spelled a couple different ways. We're just going to spell it P-A-N-G-E-A, Pangaea. So approximately 200 million years ago, this supercontinent began to break apart and drift to their current locations. Now, of course, back in 1950, nobody knew this. Nobody understood that everything used to be together at one point. So he was the first one to kind of look at the world and say, hey, all the continents and stuff kind of look like pieces of a jigsaw puzzle. If I kind of move them around, they kind of look like they fit together, like this, basically, when you see this picture here. So if this were true, if the continents were together, people weren't just going to accept it and say, oh, yeah, they look like they're together. Sure, we'll believe you. He actually had to go out and find evidence to suggest why these things were together, which is really part C for this. So what were his big pieces of evidence? Well, the first one was the one we just kind of looked at, coastlines. When you look at the coastlines, he studied the shapes of continents to support his viewpoints. He noticed, obviously, that the eastern coastline of South America matches up very well with the western coastline of Africa. And you can even see that here in this picture. But then, if you kind of turn North America on end and you slide, some of the British Isles and Iceland, some of those things, they kind of fit together. And if you put Eurasia on end, everything else kind of fits together as well. So looking at the coastlines was one thing. Some of his other pieces of evidence that he looked at that I didn't include here before we get to number 2 is he looked at a lot of the geology. He looked at the rocks of things. So he went to these locations and found out that these tracts of land that were separated by oceans, huge distances apart, had very similar rock types. Not only that, but mountain ranges. This mountain range of our Appalachians match up with this mountain range that's in Africa. Same rock layers, same order of the rock layers. To him, that wasn't a big coincidence, that it only makes sense if those land masses were together at one point. So I didn't even include that he looked at matching rock layers and mountains. But number 2, though, his big piece of evidence was looking at fossils. He looked at very large land animals and plants on different continents to support his hypothesis. Again, he didn't look at things that could fly. He didn't look at things that could swim, because people would argue, hey, those things flew across the ocean or they swam across the ocean. So he looked for very specific things. So I can kind of show you that with this picture then. Here's some of his famous fossils that he was able to find evidence of. Signanthus, which was like this reptile-type fossil he found across South America and Africa. And again, this slow, lumbering land animal, there's no way it swam across there. Mesosaurus was a freshwater organism. So again, it couldn't swim across the ocean, but he found it, in South America and Africa. The fern Glossopteris, he found all throughout all of these land masses, all 5 of them. And then Lysosaurus was another big lumbering early reptile organism that he found on a couple of different land masses. So again, you could include any of those under part 2, the ABC that's there. So unfortunately, even though he had all this good evidence, people still didn't accept his theory. So why not? Well, letter D. What major piece of evidence could he not explain? He didn't understand the mechanism. He didn't understand the what was it that could make large land masses move around. At that time in the world, 1915, people used to think the ocean floor was flat, that it was basically sand. So nobody could figure out, well, how could land masses plow through other land masses? It didn't make sense. Physically, that wasn't going to happen. So they didn't accept his theory. So along came another guy, and this is what part E is. His name was Harry Hess, Hess. So he re-examined Alfred Wegener's theory, but what he used was sonar, SONAR, to develop 3D maps of the seafloor. Basically, he was a geologist, but during World War II, he was called up to serve as his ROTC officer aboard this one naval vessel that had sonar to detect enemy vessels. But basically, he had a lot of downtime, so he would point the sonar at the ocean floor and discover that the ocean floor is kind of like continental land masses. There's mountains, there's hills, there's valleys. There's all this stuff on the seafloor, which is incredible. But really, his big discovery was number one here. It's the MOR, capital M, capital O, capital R, or the mid-ocean ridge. It's the name given to the large system of underground or underwater mountains that run the length of the Atlantic Oceans. Number two, what goes along with this then, the long, narrow depressions where two tectonic plates separate, that's called the Rift Valley, R-I-F-T Valley. So what he found out was that new magma is coming up basically at the Rift Valley. Well, think about it. If new magma is always coming up to the Earth's surface and pushing continental land masses apart, the Earth would just keep getting bigger and bigger and bigger and bigger. And that's not what happens. The Earth stays the same size because what you have to understand is at the opposite end of that tectonic plate, it's being subducted. Old continental or ocean crust is going beneath continental crust and it's getting recycled. So new stuff comes up and old stuff gets recycled at the other end. So basically what we found out is that the age of the oldest continental rocks is pretty old, about 4 billion years old. But the age of the oldest ocean rocks are only about 200 million years old. So if the Earth were all formed at the same time, you would think all the rocks would be relatively the same age, but they're not. The ocean is much, much younger than the continental land masses because the ocean's constantly getting recycled. New stuff's coming up, old stuff's getting recycled. Another thing that he didn't look at, but later scientists did, by studying rocks on both sides of the MOR, scientists have discovered that when rocks harden, a magnetic orientation known as polarity, P-O-L-A-R-I-T-Y, locks it into place. And basically, this is the alignment of the North and South Pole, the magnetism. It flip-flops through time, and those evidences are locked into the rock record. We can see that polarity shift happens all the time throughout history, and those rocks record that shift in the ocean floor, basically. So put all this together then, his ideas and later Harry Hess's ideas and then some later scientists with polarity. And nowadays, since the 1960s then, we've accepted this theory called plate tectonics. From Alfred's theory of continental drift to Harry Hess's theory of seafloor spreading, we kind of put it all together and we call it the theory of plate tectonics. All right, so you can complete the assignments then that go along with this recording and some of the other assignments below this then.